Right. In this video, we are going to look at 4 planes and with which are defined by certain conditions given, and then we're going to find some equations. Plane 1 contains this point and these two vectors. Plane 2 goes through these 3 points. So 2 points are not enough to define a plane, but a third point, as long as the 3 points are not in a straight line, then you can define a plane going through the 3 points. The third plane has got this point in it, and it's perpendicular to this straight line. The last one contains this straight line and it's parallel to this straight line. So in part A, we want to find the parametric and scalar equations of each of the planes. So let's start with the first one. So plane 1 goes through minus 1 minus 3 5. So plane 1 goes through 1 minus 3 5, and it's got these two vectors. So I'm just going to make a little sketch. So that means in this plane we've got this point 1 minus 3 5. So that's going to play the role of x naught, y naught, and z naught. And then these two vectors are in the plane. So that means those two vectors can play the role of our direction vectors m1 and m2, so long as the two of them are not parallel. And well, by just inspection, you can see that these are not parallel because the numbers are not going to be multiples of each other. If you make this -1, then these two numbers are not going to be the same as those two numbers there. Okay, so this is 2j here. So we start from the vector form of the equation. So vector form is the vector position vector of r naught, which is this point here, plus lambda m1 is going to be say this vector here, and then plus nu m2. So this is going to be x, y, z is equals to 1 minus 3 5 plus lambda. So then lambda times 4 1 minus 1, which is the first direction vector, and then plus nu. The second one is minus 1 minus 2 1 minus 1 minus 2 1. And so let's see, we want the parametric form. So from here we can extract the parametric form. So x is going to be 1 plus 4 lambda minus nu. Y is going to be minus 3 plus lambda minus 2 nu. Z is going to be 5 minus lambda plus mu. So this is going to be our parametric form of the equation of the first plane pi 1. Then we need the scalar equation. So for the scalar equation, First we need the normal vector. Okay, so we need the normal vector of this plane. Now, since we got these two vectors which are in the plane, if we take a cross product, that's going to give us a vector perpendicular to this plane, which is going to be our normal vector. So that's the first thing we need to work out. So M1 cross M2 is going to be M1 is 4 1 minus 1, 4 1 minus 1. M2 is minus 1 minus 2 1 minus 1 minus 2 1. If we work this out, it will give us minus 1 minus 3 minus 7. Okay, so that is going to be our normal vector. Now remember the scalar form of the equation says that r minus r naught, that vector dot n, which is here, we just found it, is going to be 0. So r naught has got coordinates 1 minus 3 5. So this is going to be x minus 1 minus 3 5. It was 1 minus 3 5. So these are x naught, y naught, z naught. So it's going to be x minus 1, y plus 3, z minus 5 dot n, which is found as minus 1, minus 3, minus 7. This must be equal to 0. So if you work out this dot product, it's going to be negative x minus 1 minus 3 into y plus 3 minus 7 into z minus 5 equal to 0. So this is going to be x plus 3y plus 7z equal to 27 if we remove those brackets. So that's that for the first plane. Now I'm going to go to the second plane. The second plane is just defined by the fact that it goes through 3 points. So I already mentioned that these 3 points must not be collinear. So long as those 3 points are not collinear, then we have a plane that goes through it, a unique plane. If they are collinear, then we don't have a unique plane. So that's plane number 2. So again, if we make a sketch, so if this is our plane, actually I want to call this A, B, and C. So you can have, say, A here, maybe B there, maybe C there. Okay. So we, for the vector equation, need one point through which the plane goes, and we need 2 direction vectors. So the vector equation is like this. So lambda m1 mu m2. So this is the position of a point on the plane. Well, we've got 3 here, so we are spoiled for choice. Then we need 2 direction vectors. So these we can define as follows. So the first one can be AB, the other one could be BC or AC. Any of those will work. I'll do AC. So for AB, I'll do these here. So that's going to be 1 minus 2, 0 minus negative 1, minus 2, minus 1. So this could be, this is going to be our M1. Then for the other one, if we do a C, okay, so yeah, for the other direction vector, so actually if I change my mind and do BC, so BC is going to be 0 minus 1, 2 minus 0, minus 1, minus negative 2, so it's going to be 1. So these are the 2 direction vectors that we have. So for the equation, then we can write x, y, z. We could use the first point as our x0, y0. So it's 2 minus 1, 1. 2 minus 1, 1 is the x0, y0, z0. That's the position vector of it. M1, we got minus 1, 1, minus 3, minus 1, 1, minus 3. M2 is this one. Well, I mean, of course we've got to make sure that these two are not parallel, but just looking at them, minus 1 there, and then the other two are not the same, so those two are not going to be parallel. Minus 1, 2, 1. So this is the vector form of the plane. So from there, the parametric form is going to be x equals to 2 minus lambda minus mu. Y is going to be minus 1 plus lambda plus 2 mu. Z is going to be 1 minus 3 lambda plus mu. So that is our parametric form. For the scalar form of the equation, we're going to do the dot cross product, of M1 and M2 to find the normal vector. So M1 cross M2, so that's going to be ij and k, minus 1, 1, minus 3 is this first one. Second one is minus 1, 2, 1, minus 1, 2, 1. Okay, so let's see what we're going to get here. Now, in the first instance, we have got 1 plus 6, we've got 7. For the second one, we got 3 plus 1, which is 4. And then for the last one, we got minus 2 plus 1, so it's going to give us minus 1. So that is our n. Okay, so if we do r minus r naught dot n, equals to 0. So again, if we choose our A to be our R0, so we're going to have x minus 2, y plus 1, z minus, so x minus 2, y plus 1, z minus 1, dot 7, 4 minus 1 equals to 0. So it's going to be 7 times x minus 2 plus 4 times y plus 1 minus z minus 1 equals to 0. It's going to be 7x plus 4y minus z. The constants are going to be negative 14 here, and then back to negative 10, and then that's going to be negative 9. So this is going to be equal to 9. So this is going to be the scalar equation for the second plane. The third plane is described as follows. So this plane contains or goes through the point 1 minus 3 minus 2, and then it's perpendicular to that straight line. So let me just paste this. Okay. So again, let's just sketch. So this plane, it goes through it goes through 1 minus 3 minus 2. We put that one here, there, 1 minus 3 minus 2. So it's going to be our x naught, y naught, and z naught. It's perpendicular to this line. Now if you have to, you might have to, if you have to, please go back to and check our lecture notes on straight lines in 3D. So the direction vector of the straight line here is going to be given by the coefficients of the of the parametric value. So it's going to be 2 minus 4, 3, and that's going to provide the normal of the plane. So from here we can simply find the scalar form of the equation, because the scalar form is r minus r naught dot n equals to 0. N is given through a straight line. So this is going to be x minus 1, y plus 3, z plus 2 dot 2 minus 4, 3 equal to 0. If we work this out, it's going to give us 2x minus 4y plus 3z is equal to 8. So that's that. We've got the scalar form of the equation, but for the parametric form we need two non-parallel vectors. We are going to obtain these non-parallel vectors a bit like we did here in the second plane where we had 3 points. So for this one, we already have 1 point on the plane, so we need to get 2 other points. And then from those points, we can now get some direction vectors. So we are going to extract those from the equation that we already have. We can either make the process complicated, or we can make it easy for ourselves. For instance, you can see that if we choose y to be 0, z to be 0, then x is going to be 4. So that tells us that one of the points on this plane is 4, 0, 0. Again, if we choose x to be 0, z to be 0, y is going to be 2, negative 2. So we've got 0, negative 2, 0. So these are on the plane. Of course, the other one is the one that's given, 1 minus 3 minus 2. So 1 minus 3 minus 2. So we call these A, B, and C. So that means this one is going to be C. We could put A there, we could put B there. Then from those we can get the vectors that we require. A is 2, 0, 0. B is 0, minus 2, 0. So for instance, AB, okay, AB is going to be minus 2, minus 2, 0. So AB is a vector, so minus 2, minus 2, 0. That could be our M1. Then AC is going to be minus 1, minus 3, minus 2. So AC minus 1, minus 3, minus 2. We're going to use that as our M2. And then we can write this equation, lambda M1 plus nu M2 so it's going to be x, y, z equal to point 1 minus, well, position vector of this 1 minus 3 minus 2, 1 minus 3 minus 2 plus lambda M1 is minus 2 minus 2, 0 plus mu M2 minus 1 minus 3 minus 2. So that means x is going to be 1 minus 2 lambda minus mu. Y is going to be minus 3 minus 2 lambda minus 3 mu. Z going to be minus 2 minus 2 mu. So that's going to be the parametric form of the equation of the straight line. Again, remember that the parametric forms are not necessarily unique, but if you convert them into the scalar form, then you must find the same thing. We are left with the fourth plane. So the fourth plane is defined as follows. There it is. So we have got a plane that contains one line and it's parallel to another line. Contains one line, it's parallel to another line. Parallel to one line contains another line. So imagine this is our plane. So let's call these two lines, this one L2, this one L1. So L1 is in this plane, so it's going something like that. That's L1. This point is on L1, so that point is part of our plane. 0, 3, -5. Then L2 is not part of this plane, but it's parallel to this plane. So perhaps L2 is going something like that, somewhere there. Okay, but it's parallel to this plane. So L2 and this plane don't meet. Okay, so from L1 we have got one direction vector, namely this one, 6, -2, -1. This is going to be our M1. So M1 is 6, -2, -1. M2 we can get from L2 because it's parallel to the plane. Okay, so that's going to be 3, 2, 4. 3, 2, 4. So from that we have got two direction vectors, so we can write the parametric form of the equation. Okay, using this point, so for the x is going to be 0 plus 6 lambda plus 3 mu. That's 6 and this 3. Y is going to be -2. This negative, no, going to be 3. This 3. Minus 2 lambda, and these 2 plus 2 mu is 2. Then z is going to be -5 minus lambda plus 4 mu. So that's going to be the parametric form. Since we've got M1 and M2, we can find the normal of this plane. Once we got the normal, then we can come up with the scalar form of the equation. 3, 2, 4 here. If we work this out, we get -6, -27, and 18. So that means the normal form, the scalar form, so this is our n. So the scalar form is going to be x minus 0, remember, for our x0, y0, z0. x0 is 0, y is 3, and so y minus 3z plus 5, then got minus 6 minus 27, 18 here. If we work this out, if we work this out and divide accordingly, we are going to get, okay, so this is going to be, negative 6 times x minus 27 y minus 3 plus 18 z plus 5 equal to 0. So this is going to be minus 6x minus 27y plus 18z. Then the constant is going to be 27 plus times 3 and then 18 times 5. Let's see what that works out to. So 27 times 3 27 times 3 plus 18 times 5. Going to be 171. But since it's going to be on the other side, going to be negative 171. All these numbers are divisible by 3. So if we divide by negative 3, actually, it's going to be 2x plus 9y minus 6z is equal to, so we need to divide this by 3. It's going to be 57. So it's going to be the scalar form of that equation. There are more questions concerning these 4 planes. We're going to address them in the next video. This was just part A. So there is part B, there's part C, and there's part D. Alright.